So excited to have Dylan Hadfield-Menell here to talk about his work on alignment. Dylan is an assistant professor at MIT in the Electrical Engineering and Computer Science department. He runs a group that works primarily on alignment, and I'm excited to hear about his work on inclusion today. Dylan, what would you like us to do in terms of asking questions? Hold questions to the end, to like particular points, just jump in?
I think, at least to get started, please jump in, interrupt, ask questions as you see fit. And, if it feels like there's going to be enough coming through that I may not get through everything I need to, at that point, I might ask folks to hold off. If that happens, obviously, nothing personal, just tracking time and things like that. So with that, please jump in. It's hard enough to make these things interactive remotely, so lower the barrier to asking questions if you'd like to. With that, I think I'll kind of go ahead and get started. So thank you for the introduction. As Sydney mentioned, I run a group that works on AI alignment. And, a lot of the, if you go to one of my standard sort of research talks, you'll probably see me throw up a video or something like this. And I'll tell you a story about how this is an AI system that's designed in order to maximize some sort of goal. And in this case, it's actually maximizing it quite well. It just turns out that it's been given the wrong goal. So what happened here is that the system designer told the system to maximize the overall score that it gets. And if you notice, this score in the bottom left actually is going up because of like a quirk in the scoring system that gives you points for these turbo balloons. But clearly, this isn't doing something that looks like what you might realistically want, which is kind of winning the overall race. And this is a part of a really broad phenomenon of incentive misalignment in the context of agent design. And for me, one of the basic sort of laws in this space that I've spent a lot of time thinking about is Goodhart's law. So Goodhart's law is the idea that once a measure becomes a target, it ceases to be a good measure. So by measure, what we mean is some way to represent sort of some function that captures what we care about. So we can't actually measure winning very easily, but we can get the score, and score roughly gives us probability of winning. A target, we mean setting this as the goal for some sort of optimization type system, thinking AI system, but you could also easily think, incentives or bonuses for an employee would also fit this quite well. And then when we say it ceases to be a good measure, we mean that kind of frequently when you optimize score, you end up with something that doesn't actually optimize your chances of winning. And this is how you end up sort of spinning around in circles over and over again. One sort of really brief historical aside, just mainly because I think it's kind of interesting. Goodhart didn't actually say anything that looks like Goodhart's law. This is the closest thing Goodhart said to that, which is any observed statistical regularity will tend to collapse once pressure is placed on it for control purposes, which, I mean, if you squint, it's the same rough idea here. But I think this version of it, this sort of nice, concise, when a measure becomes a target, it ceases to be a good measure, is actually part of that formulation really matters. So while I was finishing up my thesis, I went and I looked up on Wikipedia and found that actually this was credited at the time to Marilyn Strathern. But unfortunately, I didn't do my homework close enough, which is that so I cited her in my thesis, but if you go back and look even more closely, yes, she does in fact say that, but if you go on to read like 2 sentences later, she describes it to someone else. So realistically, this is really Hoskins in 1996 for this modern formulation of it, which is actually surprising that it took so long for this to become like a phrase. Like I would have thought actually that this would have been something from much longer ago. And for those of you who are at the edge of your seats worrying, Wikipedia has in fact been updated, so you can lay those concerns to rest. So when I think about this idea, and this aspect of sort of over-optimization, misalignment, incorrect incentives, I often come at this from this perspective that Goodhart's law brings, which is this long sort of, it's really a property of incentives rather than AI systems in particular. So for me, some of my earliest exposure to this area came from this paper, which is a 1975 paper on the folly of rewarding A while hoping for B, and this talked about lots of failures of human incentive systems. So one of the classic examples is this Cobra, what's called the Cobra effect, where there was a bounty given on cobra heads to reduce the wild cobra population, but people eventually realized they could just breed cobras and then kill them. And it was actually much easier and sort of very intelligently subverts the underlying goal of creating this bounty. In this setting, actually, once the bounty was gotten rid of, you ended up increasing the wild population because you released all the captive cobras out into the wild. So the problem actually gets worse, which is really one of these properties of this, right? It's not just that wrong incentives lead to sort of like, extra sort of opportunity left behind or on the table, but it's actually that over optimization and mistaken incentives sort of leads you to do very bad and sort of stupid things. An example of kind of my favorite sort of very recent work on this is called On the Iniquity of Predicting A While Hoping for B. And in part, I'm very jealous of the paper title, but they looked at healthcare and in particular prediction in the context of healthcare. So they wanted to figure out some prediction of risk for people in their system. In order to do this, they measured predicted healthcare costs. And while this seems like possibly a reasonable thing to do, of course, there still is the specification gap because the costs someone incurs are not exactly equal to their underlying health. And that gets shown in this kind of, the central figure from the paper, where the x-axis is showing how risky the algorithm thinks you are. The y-axis is showing a much looser but much more robust measurement of how unhealthy you are, which is how many chronic conditions you have. And then there are two data series, one for Black patients here in the dashed line in black, and one for white patients as the gray line, as the solid line. And the thing to read from this is at the 95th percentile sort of point of risk, basically when the algorithm thinks you're at the point where intervention is recommended, white patients have about 1.5 fewer chronic conditions. So you're prescribing care to people who are much better off. And the people who are kind of getting more lucky and getting these extra resources, that bias tends to fall across racial lines. And in this case, it has to do with sort of the history of the US healthcare system and a whole bunch of really complicated things that I won't get into here. But this is another example of a specification gap and incentive misalignment sort of leading to incorrect behavior and something that wasn't what you actually wanted. The final example that I want to talk about here is this paper from last year called Reward Misdesign for Autonomous Driving. And this is by Knox et al. And in it, they did this really clever thing where they went out and first they developed a bunch of sanity checks to have flaws in reward functions. So how can you figure out when reward functions are wrong? And then they applied these to a wide range of reward functions from the actual literature in autonomous driving. So they grabbed published papers, took the reward functions from those, and they found basically near universal flaws. My favorite one of these is their indifference points test. So basically, it's a pretty simple test. You have 3 trajectories, one where the car drives and crashes, one where the car stays still, and one where the car drives safely through to its destination. And then you can compute a number p, which is the probability at which you are willing to accept some chance of crashing. So this R of tau crash, that's the reward for crashing, plus a 1 minus p reward for driving to your destination. So p represents like the probability you crash. And you find it such that you're equal to the reward you get for staying idle. So this tells you like your risk preferences. What level of chance of crashing makes me indifferent between staying home and leaving the driveway. You can take this number and turn it into sort of an estimate of how far you'll drive before you crash. And then you can actually compare this number to humans. Here's kind of driver data to calibrate from for people in the US population. And what they find is that across these papers that they surveyed, they all have remarkably risk-averse, sort of risk-seeking reward functions. So here, to put these numbers in context, right, this is kilometers per collision. So this is saying you drive on average 1 kilometer per collision according to these risk preferences. This one says here you would be willing to drive about 100 meters and crash about every 100 meters or so. And most reward functions they looked at actually failed an even more basic test where they actually preferred crashing to staying still. They had a nice little blurb up here that I'll put up on the screen if folks want to read it. But I think, for me, I like to step back at this point and say, like, okay, what is this saying about incentives? Well, again, it's this repeated point of the wrong incentives doesn't lead to just like slightly poor performance, but leads to these just absolutely ludicrous kind of implied preferences. And two, I think if we want to be fair to the paper authors that got surveyed, they weren't building production systems, right? There was no sense in which these reward functions were ever really considered for a real car. But instead, they're meant to get papers written. And so what happens is you change the assumptions under which some reward function is designed, and you get very, very bizarre predictions. And this is kind of the underlying phenomenon that we have. So when we think about over-optimization, there's a couple of different things that people have done. One paper that I like to point people to is this one called Categorizing Variants of Goodhart's Law, which does a good job of laying out different mechanisms through which Goodhart's Law operates and ways in which it can kind of lead to a separation between your proxy objective and the real objective that you care about. And so when we look at the state of the science and the answer to the question, why is Goodhart's Law pervasive, we've got examples of kind of lots of documented examples of misalignment in both now, I'd say, human and AI systems. And we've got some theory and categorization of mechanisms, kind of ways in which you have misalignment getting operationalized. So we have lots of reasons why Goodhart's Law can happen. But what's missing is this story of why is it seemingly inevitable? Why is it always the case that optimizing for the wrong reward function kind of leads you astray? And this is, I would say, one of the central focuses that I took on as a researcher, kind of finding my way through a PhD program. One paper that really shaped a lot of things for me was this paper called Should Robots Be Obedient, which was published in 2017. In it, we kind of wanted to look at this very simplified example of a robot that was learning about your rewards over time and think about what are the cases under which it should do something different than what you asked it to do, and when is that beneficial or not. So we looked at things like the probability the robot takes the action you asked it to take. So that's what this notation here, AR and AH represent. Over time as the robot's learning about goals. And what we find is over time, it is less likely to do what you asked it to do because in our model, the human make mistakes. So, you correct those mistakes. And similarly, fixing those mistakes gives you kind of increased utility. So this gives us kind of the real basic setting of having the correct model. What we did next really shaped a fair amount of my next research direction, which was we took a look at this game when you have missing features. When there's aspects of the sort of value of different options that a person's asking the robot to take. And there are things that the person cares about that the robot doesn't have a representation for. It doesn't have a way to measure exactly. And we find there, we can plot the results of here the probability that the robot does the action you asked it to take. And look at this as we have missing features over here on the left and added distractor features on the right. What we see is even in the very first round of the interaction, something kind of bizarre happens, which is that only 25% of the time does the robot do the action that the person asked it to do. This is the first interaction. There's an uninformative prior. This shouldn't really be happening, and we actually thought it was a bug when we looked at it. But it turns out if you only observe one feature, you either want to maximize it or minimize it according to our model. So what happens is you give the robot some information about whether you should maximize or minimize, and then it takes that information into account, ignores what you asked it to do, and just does the maximization or minimization. And as you go further, and so as you have a more long interaction, what you can see is that this missing feature is sort of over kind of disobedience or doing something other than what the robot was asked to do continues to persist at a suboptimal level. So this got me along the line of thinking about missing features in the context of reward functions. Maybe there's something that relates to the sort of likelihood of Goodhart's law being predictive with this constant setting of being able to measure only a subset of the things that we care about. And this is what led to this paper called Consequences of Misaligned AI in NeurIPS 2020. We looked at this. We had a very simple model that captured this basic idea. We've got a system designer with a true reward R star, a proxy reward R tilde, and the central assumption we're going to make is that R star depends on more features than R tilde. So that's what we mean here with L greater than J. And we also introduced the idea of a shared resource constraint. So what you're doing here is you're allocating resources across different things that you can measure that could be either good or bad. So as an example problem, we pulled up something from social media where we said that the features that you care about optimizing between are maybe the different clicks that you get. So how much direct shallow interaction do you have? Maybe some more sophisticated measurement of engagement, some idea of the prevalence of hate speech overall, so here increasing further in complexity, and then maybe something like community well-being. And the shared resources you're allocating, you could think of as being something like user attention and space in the user's feed. So we put together this model of the problem, and then we set something up where we're optimizing for two of the things that we care about, and we care about all four. And what we find is not terribly surprising. You see that as you maximize proxy utility, it goes up and up and up as time goes on. And your true utility hits some local maximum and then falls off over time. And this is that specification gap that we're looking at. So this is what we see as we simulate a version of your model. But, did I just cherry pick these? You'd be perfectly reasonable to criticize. What I'm showing you here, is this actually some phenomenon, or is this some cherry picked set of numbers to tell a story? Well, at least for this particular problem setting with 4 things that we actually care about and only 2 that we're able to measure, I can tell you that I didn't cherry pick anything. And that's because for any selection of proxies that you pick, for any subset of things that you measure, eventually you stop increasing true utility and you start decreasing it overall. And what we go on to show in the paper is that actually for a really broad category of these types of problems, this is always going to be the case. More concretely, if we have a utility function R star that depends on L features and a proxy that depends on J with J less than L, and then a state space that consists of states in RL with some sort of resource constraint that controls feasibility, then if we look at the maximum state we get to by maximizing the proxy reward, we find that this condition over here, which I'll come back to in a second, is predictive of a regret, a sort of maximum regret that you can incur from maximizing your reward. Basically, this term here says that there is always going to be some sort of set of environmental bounds such that your maximum utility you could actually get minus the true reward you get for the state you wind up at is greater than some R minus. So we find that maximizing your proxy utility will essentially always leave you worse off than you started out by. And what prevents that depends on things outside of the optimization. So it's a really fun paper, and I actually recommend going and taking a look at it to get a sense of the specific math. But at this point in the story, the thing that this really shows, and that for me really sort of drove things home, was some of the answer to why do we see Goodhart's law so pervasively? So why are incentives so brittle? And this result in English basically shows that it stems as a consequence from incomplete value measurement, so caring about a lot of things and only being able to measure a subset, and then shared and limited resources that have to be allocated across these measurements. And when this is the case, you expect that optimization eventually leaves you worse off than where you started off. And I'll say that, sort of technically, these are probably sufficient, but not necessary. So I could imagine there are other settings where you would have over-optimization, but certainly this one in particular, incomplete value measurement and shared and limited resources. This is one of the key ones that we found. So this kind of actually leads to a secondary question, which is, okay, so if incentives are so brittle, why is optimization everywhere? So, we're talking about Goodhart's law, misalignment. It's usually the case that over-optimization kicks in at some point. It's very hard to get incentives right, yada, yada, yada. So why do it in the first place? And the answer is because it does still kind of work, or rather, it sort of works until it doesn't. So if you look at this plot again, what's really happening is there's kind of like two phases of this optimization. In this first phase over here, what's largely happening is you're reallocating resources between the things that you can measure. So you can measure a couple of things that really sort of like matter overall. Maybe in that sort of recommender system setting, you're able to measure something about sort of, very simple engagement, as well as like how many times someone shares links or something like that. And what this initial phase will do is it'll reallocate, it'll optimize the system so that it kind of like gets people to balance their efforts correctly between those two things. The problem, and that often is quite valuable just as a starting point. The problem is that once you hit something like Pareto optimality, so you're allocating between those two things, and you hit Pareto optimality between them, that's when you move into what I call the extraction phase of optimization, which is to say that there's only one thing left to do to increase your proxy reward, which is to take resources from the things you're not measuring and reallocate them to the things that you are. Because from the perspective of the optimization, the things you're not measuring are kind of like free lunch. There's no cost to taking resources from them. So it's kind of cheap and free to reallocate them to the things that you are measuring. And the thing is that typically by the time you sort of hit this point, it can be very hard to stop, right? So in human incentive systems, for example, some of the people who are being paid to make the blue line go up, right? It's going to be very hard to get them to change their job when sort of making their income and providing for their family depends on that number going up, right? These systems are often quite sticky. And so in human settings, it's usually the case that you're kind of, you get locked into this. In the context of AI systems, it's more just that you have inertia in the context of complex systems. The things that you're measuring are the things that you've spent money to try to measure, and it takes time to update them. So the moral of the story from roughly maybe the first half of the talk is with optimization-driven systems, you get what you can measure, and eventually that's going to come at a cost to something that you can't. And this is maybe one of the big takeaways and lessons that I had from working on my PhD. And I think this is one of the big sort of things that drives concerns about misalignment in the context of AI systems, right? If we have powerful AI systems, according to these arguments, we probably won't be able to represent everything that we care about in the goals of those systems. If those systems are modeled as sort of rational optimization of proxy metrics, eventually bad things probably happen. At least that's the story of the argument, or at least the one that makes sense to me. So, what can we do about actually fixing that and measuring more? Well, the idea in the AI safety community kind of comes down to, well, let's get better at measuring more things. Let's make it easy to measure complicated things so we don't end up optimizing for shallow, simple, easy to measure things at the cost of complex, sort of maybe more difficult to measure but valuable things. And this is the idea that led to what I'll call the backflipping robot. So maybe some of you recognize this video. This is from I think 2017. But this is an excerpt. This is taken from the paper, which is called Deep Reinforcement Learning from Human Preferences. And this is kind of the paper that I think in the modern era really brought in this paradigm of collecting human feedback, using that to train a reward predictor, and then optimizing that predicted reward via some form of RL algorithm. And how did they actually do kind of learning a reward function? Well, if you have two different trajectories, you can basically say that trajectory 1 is preferred to trajectory 2 if the sum over all of those states, the cumulative reward across all those states is greater than 0. And then you get to this probability distribution, which is called the Bradley-Terry model, if you're interested in that. And this probability distribution, this form allows you to, without too much difficulty, optimize a reward function based on this data. And so you can collect data that looks kind of like this, left is better, right is better. And in this case, rather than sort of bad answers to prompts, which you'd see in the case of language models, you actually get these weird wiggles between different motions, and you have to try to guess which one looks more like a backflip than the other. Worth pointing out that this is very bizarre to do in the robotics context. It's still a little bit bizarre, I think, in the context of language models. Many of the comparisons you're getting, because they're between things that are just bad responses in the first place, many of those comparisons, I think, are actually very strange to collect preferences between. So and maybe that's just a loose comment on the method. But of course, this method's not actually brand new, and I think give a shout out to Nate Lambert. Don't know if he's here, but if you're there, hi Nate. But I think this paper on sort of history and risks of reinforcement learning and human feedback is a really great thing to look at that traces out some of these kind of different historical traditions that lead into it. For me, I always like to highlight Brad Knox and Peter Stone's paper from, I think, 2008 on training an agent sort of manually via reinforcement learning. As you can see, it's actually got all of these standard things. The only difference is really there's supervised learning for the reward model rather than comparison-based learning. In language models, of course, this I think really took off in the Steinen et al. Paper that applied this to summarization for Reddit posts. And here they're applying your same basic method where they're collecting preferences, in this case between summaries, and then training policies based on that with PPO. And I think the key thing that kicked off a lot of where we are now is that this method was shown to sort of lead to very substantial improvement over direct pre-training or just supervised learning on its own. Right, so this is basically saying, hey, we can use this technique to pretty effectively encode what it means for a summary to be effective, and then optimize against that. And so you might hope that this solves problems from over-optimization. Of course, it doesn't actually. So here's, as we know pretty well now, when you collect these preferences, you have to stay pretty close to the baseline model you collected them from. And as you move further and further away from that baseline model, you can see that your predicted performance goes far up, but your true performance actually crests and falls off. So this is kind of like a stopgap for over-optimization. Makes it easier to measure things, but you still have the same problems overall, right? There's not really going to be a free lunch in this setting. There's been some interesting work that I'll highlight really briefly on scaling laws for reward model over-optimization. That kind of looks at some of the ways in which this over-optimization for binary comparison data specifically relates to how far you can optimize before you need to collect new data. So the next thing that I sort of want to talk about is, well, so we've got this idea, over-optimization is still a problem. What can you do about it? Well, the thing that we've been trying to do, and something we looked at recently in our paper, is, well, can we try to account for some of this hidden context directly within the method? And so by this, what I mean is that there's a central assumption within sort of RLHF, which is that your preferences only depend on the quality of the summarization, and they don't depend on things that you don't observe directly that are inputs into your reward model. So this could be things like the annotator mental state, annotator demographics, maybe there's some disagreement over performance. It could be additional information that the annotators see that's not represented to the reward model, or this could just be things like survey design changes over time. So what we did is we actually looked at trying to model some of this hidden context. We proposed a pretty simple change to the preference learning setup. We said that the probability that some alternative A is preferred to an alternative B is really the expectation over some observed context, some unobserved context Z over a utility function that depends on A and Z as well as B and Z. So the key idea is we're going to try to represent our observed preference data as an expectation over some unobserved context. And then we can ask interesting questions like, does RLHF recover the expected utility function? And we actually thought we were going to get to a yes here. It turns out the answer here is not always. So if you look at this kind of a setup here, let's say that A and B are both in the interval between 0 and 1, and that Z is a binary variable of some kind that's got equal probability over both outcomes. Let's suppose that our true utility function depends on the alternative and that random context like this. So our utility function is equal to A if A is less than 0.8, and it's equal to 2AZ if it's bigger than 0.8. What does this tell us? Well, it basically tells us that the expected value of utility is just a linear function equal to A, but up in the sort of top region of the space, there's a lot of noise over how good things are. Things can either be really good or really bad. And what we find there is that you have your true utility function, which is this linear function here, but something like RLHF will end up optimizing a reward function and recovering a reward that looks like this. So you see there's a kink here, exactly at that 0.8 where you get more variance that comes in. And in the paper, we're able to show that this learned utility function actually aligns with a social choice function called Borda count, which we show here as BC. How can we actually go about counteracting this? Well, in this context, the thing that you really need to be able to do is to model the fact that there is a distribution over utilities for each alternative rather than a single one. So we propose something really simple here, which is rather than directly outputting a single reward function, a score for each trajectory in the context of RLHF, we can replace that with a distribution over score functions. And then we take an expectation over the classification probability as a consequence of this. This ends up being a really simple change to the loss function and a small change to the architecture for the models. So the first thing that we do is you can just output a mean and a variance for a Gaussian, right? This is just saying our score is a Gaussian with some mean and variance sigma. And the other option we looked at was outputting a discrete distribution over fixed rewards. For those of you who have seen distributional RL, this looks kind of like that. And in this case, you have a classification over rewards, in this case, maybe evenly spaced from -1 to +1. What happens when we use this change is we go from learning a utility function you had here that has a different maximum to learning a utility function that is monotonic in A, which is a good thing, right? So on average, this means that we're not actually going to hit the wrong optimal point. And what you can see is we've actually done a very good job of capturing this high variance in this top region. This is also true for the categorical approach, where we get a really nice kind of linear increase where values are put into bins pretty evenly up through this lower region. And then in this top high variance region, we have an even distribution across really good and really bad for outputs there. You can use this to do some jailbreak detection, but overall, this is kind of a step in the direction of improving RLHF and doing a better job of trying to capture some of these incomplete, unmeasured aspects of what's going on. Of course, I don't want to give the impression that I think RLHF is a silver bullet by any means. If you're interested, we wrote a really long paper with a whole bunch of co-authors talking about lots of challenges with this system overall, this being sort of one of many. So please go check that out if you're interested. At this point, we're nearing the end of the talk, and we're sort of getting through what I'll call the more technical component of things, where really, you know, I've got this story that I've been working on that represents maybe almost not quite a decade, but working on a decade of consistent research for me, which is capturing this idea of incomplete optimization and the effects of over optimization. And, you know, I think really starting a couple of years ago, but I would get this sort of feeling kicking in the back of my head that there's something that's missing from the standard picture that I present to folks, right? We're talking a lot about, well, you've got some AI systems, you care about lots of things, you can only measure a subset, and it's hard to measure everything that matters. And well, you know, the designer really wants to do the right thing, but they just sometimes don't, or they just, you know, they're not able to measure everything that matters, or something like that. And, you know, I would provide examples of how this would work, and I was spending time looking at reward engineering across the industry. And one thing that I found and looked at was, if you looked at actually in recommendation systems, this process for managing and adding new things that you weren't well represented for the goals of your system actually was relatively well understood. Not written about in theory so much, but there were clear processes in place at basically every large social media platform to figure out what you're missing, start measuring that, and start optimizing it, and to actually do that really effectively. So what was kind of missing in the story? What was like the big elephant in the room? Well, the thing that was really there is that all the time we have tons and tons of stories of tech companies knowing about problems and even maybe having somewhat measurements of problems, but choosing not to measure them or modify their systems based on it. And for me, a sort of really big thing that drove this home was the Facebook files, which was a series of leaks that came to the Wall Street Journal from some Facebook employees. And in these files, what they cataloged were lots and lots of examples of exactly this, right? Things that were potentially harmful for users, so things that mattered in some moral or value-based sense, but that weren't being valued highly within the company, even when they were aware of it. So this story of, well, we're just not measuring all the things that matter because it's just too hard, just doesn't actually quite fit. And it was stewing over that realization and looking actually at this consequences of misaligned AI model that pushed me in a slightly different and new direction. So this story here, right, I presented a mathematical model and I gave labels and semantic meaning to each of the variables. But that can be easily changed without changing any of the real mathematical conclusions. So what happens if we take this model here, and rather than thinking of it as these features, which are maybe different features about what Mark Zuckerberg cares about in the context of Facebook, instead, we can think about these as features that capture the preferences of different individuals, right? So the first feature is maybe Maya's ecosystem preferences, and Alex's ecosystem preferences, or Marcus's, and so on and so forth. And what's happening here is we sort of shift a little bit of what the model feels like and what it means in a very real sense. Because now, when we look at this plot, it has a really different sense to it, right? This story of resource kind of reallocation followed by resource extraction, I mean, it doesn't sound good when the extraction is coming from different things that I care about that I didn't get around to measuring. But it's particularly bad if you have that extraction here is really coming from things that different people care about that are not represented or well measured. And so the conclusion of all that math that I kind of walked everyone through earlier is that when we look at it, in this context from this more pluralistic perspective, if you're excluded, it's not just that you won't get the benefits of optimization. It's not like you're just left out and you're missing out on an opportunity, but it's that you can actually expect that your values will be harmed by further optimization. Because your desires or what you care about is not being included in every place where the people whose values are being well measured are included. Every place where those values disagree with yours, you should expect you're going to lose. And because of things like Goodhart's law, you should expect that it's not just that you'll lose, but it's that you'll lose badly. So what it came down to was thinking about this idea of values for humans and across society as being broken down into a type of matrix where the measurement order of like how you enumerate and learn through the different values of this matrix really matters. So the way that I've started thinking about things is that we have kind of a matrix with, really think about it as having an infinite length, infinitely many columns and infinitely many rows, where each column represents some different feature that you might care about in your value function. Right, so every feature here, as we move further and further to the right, we're moving to more and more complex different inputs to my reward function or my value function. On the other hand, going down the rows, we can think about how each different person incorporates those features into their reward function. So imagine, if you imagine that these reward functions have linear dependence on these features, then each row really represents my particular linear combination over those features. And what matters is how we go about adding new features into this matrix, how we explore and identify these rows. And unless we actually pay attention to enumerating both of these, we'll never get all the way through them. Right? So if you focus all of your attention in sort of for a small subset of people or a small subset of things that matter, you end up kind of taking resources from these other regions and reallocating them either to the left or sort of up. And if you remember kind of like computer science theory, like any of those kinds of proofs, you'd sometimes get to these things where you have these infinitely long matrices. Even if you go back to the proof that like the rational numbers are countable, for those of you who remember those kinds of diagonalization arguments, right? The way that you do that proof critically requires that you enumerate all of the numbers in this large matrix in this kind of crisscrossing pattern, where you sort of work your way down the rows and then you sort of dovetail through the columns and continue to iterate all the way through it. If you only get stuck on one particular row, you may never get down to the things down below it. And I think there's something that's true in an analogous way in the context of AI safety and value alignment. What the order is through which we add more things to what we're measuring, or different representation of different features of value for different people, really matters. And if we only spend our time sort of adding more columns but not more rows, that actually might be more harmful in a kind of perverse way than we'd realize. And what do I mean by that more specifically? Well, if we imagine that we're sort of in a world where this is kind of what we've measured so far, and then we continue that we're going to expand out sort of directly along this direction, well, it actually means that it's worse off for these people down here, perhaps, as you get better at moving this way in a kind of perverse sense. And that's because if you're building a system, you're not going to deploy it unless you can do a good job of measuring what you care about. So for the people at the top here, they want to move further down along those columns, and they need to maybe hit some number of these columns before they'll choose to deploy. And if you're down here, well, you don't care if they're leaving out what you care about because they can't measure it or because they won't measure it. It kind of just doesn't really matter for you. So if you're the real kind of conclusion that you get here is that if you're excluded, technical progress on single principal value alignment is threatening, because the system designer who's specifying this proxy is sort of, maybe a little bit more sinister in some sense. And I think the part of this that I find compelling and interesting is that this follows from exactly the same mathematical arguments that support the idea of existential risk from misaligned AI, right? The inability for us to get powerful systems to be aligned with us as an individual developer is very similar to people who are just outside of the organization's developing systems that are unable to get them to listen to and kind of care about that sort of potential risk and output. So with that, I think I've got a couple of things here that are sort of recent work in the space that I think is exciting that I might want to highlight. But first, I want to recognize we've got about kind of 10 minutes left. So maybe I'll pause here for questions, and we'll take things from there. So thank you all very much.
This is such an amazing talk. Thank you so much, Dylan. I loved all the insights that come along through different recent literature, including your own work, and really, really great. I have a bit of a meta question with your approach to learning the distribution of preference.
Yep.
Seems like just the right idea. Though I suppose learning the distribution in itself could be a bit of a challenge, especially if you're going to parameterize it. I was wondering whether you noticed any unexpected side effect coming from it.
So I think we're still there's only one paper we've done investigating that method so far. So I think there's more that we'll learn about kind of over time. In fact, the main challenges we ran into there have more to do with the fact that they assume certain levels of independence in the scores between different alternatives. So if you want to use this in order to sort of identify competing objectives, the model will sort of identify that there are competing objectives, but it won't recognize that either A and B are better than C and D, or C and D are better than A and B, rather than just sort of independence kind of creeping through. So I think modeling those sort of correlated shifts is something that's interesting to explore and is a shortcoming of the method we've got there. And I think it relates to this question of parameterizing the uncertainty, right? I think the thing that this doesn't do is say, well, really, there's how different people have different sort of beliefs about how polite the language model should be. And there's this feature called politeness, and people disagree on that. And we should actually be kind of personalizing models on that dimension. So I'm pretty excited as like a complementary direction to explore some of these methods for inference time modification of models. Okay, inference time alignment, either through explicit parameters. I really like SteerLM as an approach. We're thinking a bit about some things that build on top of it. I think that direction is a really promising one to look at. And I see it as complementary to this. It's kind of like you measure everything that you can, and then at the same time also add in some safeguards to capture the fact that you're not measuring everything that you care about.
Yeah. We're kind of exploring some other inference time approach to pluralistic alignment. But going back to the meta question, I wonder, a related question I had was, I really liked how you framed RLHF as, before RLHF, if we just have like some features that we are measuring, we always miss out the unmeasured features that we are not optimizing. And I really liked how you introduced RLHF as a means to maybe mitigating that problem. Though I wonder always, it seems like when we go with this RLHF style approach where now we have a lot of data points from which we're going to learn what humans wanted from the data, there's always this question of spurious explanations about a particular subset of the data that happens to be the training data set for RLHF. And any thoughts on like how to get the right kind of data points that because data, if data is skewed in a way, you can always end up learning incorrect features that were implicit in that data set.
Yeah, no, I think this is, for me, the two things that jump out in terms of like unhappy correlations in RLHF are length bias and sycophancy, which I think length bias is fairly common, but really briefly, sycophancy is, some version of RLHF models seem fairly reliably to try to suck up to people. And if you, one of the ways they've shown this is you say, critique this argument. I think it's a good one, or I think it's a bad one. And if you say you think it's bad, the model's very likely to agree with you. If you say you think it's good, the model's very likely to agree with you there. So it's really interesting for me to think about where some of these come from. I mean, length bias, certainly it could be related to people, or it could just be sort of like other sort of correlations in the way the data is generated. Sycophancy could also be very much something fundamental about human feedback, but also could just be that that's what raters think people want, right? A helpful assistant should suck up to you is not an unreasonable interpretation of some of the instructions. So, I think trying to balance those out, the basic way, the first way you try to balance them is change what you're measuring, right? So figure out, if you want the model to be less sycophantic, give better instructions to your labelers is the first thing that I think we should be better at trying to do. And frankly, this is where the fact that private companies have done a lot of this work, I think really holds back those of us in the public space, which is part of why I'm very grateful to things like Reward Bench, actually. The second thing, and this is something we're looking at within the lab, is trying to tease out a little bit more of what models actually learn from their data. So can we come up with either identifying some feature representation that models have identified that we can actually go through and try to sort of assign labels to? So these are things like sparse autoencoders, for those of you who've seen things like that. But more generally, just trying to interpret the learned representations of models to figure out what features they actually have. And you can do that both for generation models, which is mostly what people have looked at so far. But I think actually it's going to be really valuable to do this to reward models. So being able to look at explanations and interpretable representations of learned reward models is something we're starting to put a lot more attention into. And I think is just a really a valuable tool in this space.
I had a question, sorry, about the sucking up behavior that you mentioned, that you said could be disentangled to be either the alignment data or the way, like what the raters prefer. If it were the raters, like people are seeing, especially with the new Claude model, the Sonnet that came out, that it has a different kind of characteristic. It's not that verbose or that hedgy or suck-uppy. It's kind of like very concise. You tell it to do something, it does it. It doesn't appease to you, but it also, it doesn't propose many different things that, or like it doesn't hedge. If it was, like, how much do you think it's the raters that are different, or it's the instruction tuning that is different? And do you think with the open source models that are available, like we could ever really understand what is going on with the commercial models in terms of the way the RLHF is working? Like, is there a secret sauce, do you think? Because they are different. They're very different from, Yeah.
So I guess to the first one, I would and this is pure speculation to be clear, but for the anthropic setting, I would guess that it has to do with really more changes in instructions to the labelers, whether those are sort of like AI labelers or humans, and choosing kind of what to prioritize there. I think, in terms of whether or not we can understand what's going on in private models from looking at openly available things, I think to some extent, yes, I actually think so. I think we will be able to piece out information about the kinds of biases that are present in reward learning and the types of features that are learned. Like I think, sycophancy is present in several of these models, and I expect that if we look inside reward models, we'll find the different things that lead to this observed behavior. And so I am hopeful there. But I think the second thing that I would really love to see is much more some forms of structured access to closed models in this space. I think that more transparency around reward models from developers would be really, really helpful, and is something we should push for, both as academics, but also just in the context of like regulators and policymakers broadly. Like it's very helpful to know what a model is supposed to do, and I think reward models are a really nice way to get at that question.
All right. Thank you so much. Thanks. That's a very good point. Thank you.
Thank you.
This is super great. We're like thinking about similar things from like coming at them from somewhat different perspectives. So really cool to see this work. One of the things that I'm really interested in hearing your plans for, we can find another time to talk about this if it's a longer conversation, is whether and how you're thinking about measuring more people's preferences. Is that like part of the work that your lab is engaging on? How do you figure out how to measure preferences? How do you figure out what people you're missing? Or is that, do you feel like, work for other people? That's like one question on my mind. Another is a bit more theoretical, but have you grappled at all with the problem of the incommensurability of values? So this is something that like plagues a lot of my projects right now, and it comes in like a couple of varieties. One is different values, either within people or across people, can't necessarily be traded off against one another in a straightforward way. And a lot of these models simply assume that there's like one kind of utility function that all values can be kind of projected onto. But that like itself is like a massive assumption and like a big question in both social choice theory and in theories of moral philosophy. But also you might think that like different people's preferences can't necessarily be traded off against one another in a very straightforward way. Anyway, just curious how you think about that.
Right.
Yeah, they're good. Yeah.
Maybe I'll get to the first question there, which is, the question of how do we actually represent sort of like more people's values, and what are some of the techniques that we can explore there? I think so one thing is inference time alignment methods. I think figuring out how to do that in a structured, reliable way is a really, really interesting direction to explore. I also think that some of these, there have been a few techniques basically coming out from some of the bigger labs, and my lab's also tried to do some things in this space of participatory kind of design of RLHF targets in one way or another. So these are actually some of the slides that I slipped over, but there's a collective constitutional AI, which is this paper from Collective Intelligence Project, as well as Anthropic, where they kind of designed a constitution for constitutional AI collectively. There's also this paper from, this is from the DeepMind folks, where they looked at kind of like more of a focus grouping kind of approach, where they basically brought in kind of experts or people, representatives from a particular group, and think through things like, how do we kind of elicit norms across different outputs and actually develop kind of, rule sets and things like that. We currently have a paper that's under submission at AIES that looks at doing this, basically building on this idea called constructed grounded theory, which is a qualitative data analysis method. So we basically have people go through and do this process and sort of learn a feel for the data, and then this allows them to kind of, in a focus group, decide what things should actually be measured and sort of identify axes for something like inference time alignment, which I think is a really interesting direction to look at. So yeah, thanks for letting me get to those slides.
Awesome. Any other questions? Okay, well, we're a little over time, so thank you so much, Dylan. This has been awesome. And folks can feel free to reach out to Dylan if other questions come up. And thank you so much.
We do to hear more, and thank you all for coming. It was great having you present.